Alrighty, guys. Good morning and welcome back. Today is our last day in MAC 1140, and on this last day, we are going to finish our discussion of matrices and their connections to linear systems. There will be an extra lecture posted between now and the final that has some notation information, things like that, around a collection of objects called sequences in series, which I believe deserve a little introduction, because you'll be seeing that notation in calculus only in a few places, but when it shows up, having seen that notation is a really, really helpful thing. Not every pre-calc class gets to that topic, but I do try to always get it into mind, because I think it is one of those things that's just hugely beneficial to have seen at least once before you have to work with it in calc. Sorry, I apologize. I'm a little under the weather this morning, but that's all. So today we're going to go back and finish our discussion on matrices, linear algebra. This is 40 section R1, which is pre-calc, and today is December 1st, 2nd, and it's the 1st. Today, I'm going to talk about matrix versus solving the matrix equation X equals B. Just a little announcement for anybody who missed the discussion before. Exam 4, your last midterm, not the final, but exam 4 will be posted as a take-home. Later today. Please follow the instructions carefully. Okay. Very, very important you follow the instructions, because if something goes wrong right here at the very end of the term, there's not a lot of time to go back and try to fix things, or that sort of stuff. The take home will be due at the start of the final. Final exam for your class. Just a little reminder. Final exam for your class is the 6th, which is on next Monday, I believe. Yeah, the 6th at 8 a.m. That is this next Monday. So last time we kind of expanded our understanding of matrices and their connection to linear systems. We had seen previously that you can take a linear system and write it as an augmented coefficient matrix. We can reduce that augmented coefficient matrix using row operations. And once you get that augmented coefficient matrix into triangular form, or if you're wanting to do all the work in matrix land, into reduced row echelon form, you can solve the system. If you're in triangular form, you can write the system back down and solve it by back substitution. If you work with the matrix until it is all the way into reduced row echelon form, then you don't need to do any back substitution. You can just read off the solution from that reduced row echelon form of the augmented coefficient matrix. Kind of the big thing last time, after learning how to add, subtract, and multiply matrices, we discovered that a linear system can also be written as a matrix equation. So that's where I'll begin today. So I can start with the linear system. A concrete example. I really am sorry. Rough. A concrete example of a linear system here. Okay, let's do it. We'll do a 3 by 3. 3 by 3 is the right size to work examples of here. So we'll take the linear system, for example, 0x minus 2y plus 2z. It's equal to 12. 3x plus y plus 3z is equal to -2, and x minus 2y plus 3z is equal to 8. And write down the coefficient matrix, which is just the matrix of coefficients from the left-hand sides here. We don't write these guys. That's the augmented coefficient matrix. So we just want the regular coefficient matrix 0, -2, 2, 3, 1, 3, 1, -2, 3. Say 3 by 3. I can write this and then choosing B as the right-hand side, a column, 12, -2, 8. And letting x be the column of the variables I'm trying to solve for, x, y, z. I can rewrite this system as the matrix equation A times x equals B. This is what we saw at the very end of class on Monday, that if you write out this equation, right, this matrix times this, this matrix times this matrix equals this matrix, then when you carry out the multiplication on the left-hand side, you get this thing as a column. So you'd have this thing as a column or a single matrix is equal to this thing, which means that each one of the rows, right, each one of the entries must be equal to each other. So this is equivalent to our linear system. Today, we want to learn how to solve. this matrix equation, which basically means we want to learn how to divide by this matrix A, right? If I've got like AX equals B, and these were just regular variables or constants, then I could solve for X by dividing both sides by A. So in essence, what I want to do is learn how to divide by a matrix. And that would give me X equals, we don't write it as division because there actually is no division for matrices, but A inverse times B, right? And that would be the solution, because the matrix X here, this 3x1 matrix, has as its entries the solution to the system. So once I've isolated this thing, I just look at its entries, and those are the solutions to the system. All right. Dividing, like I said, by a matrix really isn't something that can be done. But we do have a notion of multiplication, and we kind of know how division and multiplication are connected. So we're going to think our way to that, or the closest thing we can to that. But first, I need to tell you about something called the identity. In the real numbers, matrix inverses, and the identity. The identity matrix. In the real numbers, we can do division. And when you divide a number by itself, you get 1. So in the real numbers, for any non-zero number, call it little a, we have a times 1 is equal to a, which can also be stated as one is equal to, if I multiply both sides by the reciprocal of a, like this. And normally the way we would say you go from like this to this is to divide both sides by this number a here. So if you multiply any number by its reciprocal, you're going to get 1. And that's kind of the key idea to understanding what a reciprocal is. This is called the multiplicative inverse of this, right? Like 1/2 and 2, or 3 and 1/3. The number 1 is involved in defining what a reciprocal is. You could either say the reciprocal is 1 over a, and that works fine in the real numbers. But here we want some equivalent way of discussing that doesn't involve explicit mention of division. So instead of saying, the reciprocal of a is 1 over a, I can say that the reciprocal of a is a number such that when I multiply by a, I get 1. to define the similar concept for matrices, we need a matrix version of the number 1. And this is called the identity matrix. The identity matrix should have this same sort of property, that if you multiply any matrix A by the identity, you get A back. It turns out, so there's a different identity for each size. They'll always be square matrices. And it turns out that the matrix which does the job here, I2, the 2 by 2 identity, is the matrix 1, 0, 0, 1. I3, the 3 by 3 identity matrix, is 1, 0, 0, 0, 1, 0, 0, 0, 1. You can probably see where this is going. I4, the 4 by 4 identity matrix, would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's the thing that was on the left-hand side when we fully row reduced one of our augmented coefficient matrices. I suppose I1, if you want to, would just be the number 1. So this matrix has the property that if you multiply it by any matrix that you can multiply it by, you will get that same matrix back. For example, if I take A to be that matrix we were just playing with, let me just grab a different one. For example, if A is 1, -2, -4, 2, -3, -6, -3, 6, 15. Then I claim if I multiply A by the 3 by 3 identity, I will get A back. And I could do it on either side. Remember, matrix multiplication is not commutative. So we would want to check on both sides. One moment, guys. All right. Sorry about that, guys. Like I said, it's been a difficult morning here. Okay, so what we're trying to understand is the matrix version of the number 1. Specifically, a matrix such that when you multiply any matrix by that thing, you get the original matrix back. Because matrix multiplication is something you can only do if certain size restrictions are met. There has to be an identity matrix of every size. They're always square. So the 2 by 2, 3 by 3, 4 by 4 identities. I claim that if you multiply this by any matrix you can multiply it by, then you will get that same matrix back. Right? So certainly you can multiply this by another 3 by 3. You could also multiply this by a 2 by 3 on the left, or a 5 by 3 on the left. You could multiply it by a 3 by 2 on the right, or a 3 by 5 on the right. Anytime you do such a matrix product, you will get back the original matrix. And that's what I'd like to demonstrate here. So we know when we multiply these two 3 by 3s, the result will be another 3 by 3. If I want to find the entry that goes in this first position, I take the first row of the matrix A and the first column of this matrix. So it would be 1 times 1 plus negative 2 times 0 plus 0 times 4. If I want to know what goes in the first row, second column, I would take the first row of A and the second column of B. So that would be 1 times 0 plus negative 2 times 1 plus 0 times 4. If I want to know what goes in the 1, 3 position, I take the first row of A and the third column here. So that's 1 times 0, negative 2 times 0, negative 4 times 1. If I want to know what goes in the 2, 1 position, second row, first column, I take the second row of A and the first column of the identity. So that's 2 times 0 minus 3 times 1 minus 6 times 0. In the 2, 2 position, I would take the second row, second column. That's 2 times 0 minus 3 times 1 minus 6 times 0. And in the 2, 3 position, I'll take the second row, third column. That's 2 times 0 minus 3 times 0 minus 6 times 1. Finally, in the third row, negative 3 times 1, 6 times 0, 15 times 0. In the 3, 2 position, third row, second column, that's negative 3 times 0 plus 6 times 1 plus 15 times 0. And in the 3, 3 position, I take the third row, third column, negative 3 times 0 plus 6 times 0 plus 15 times 1. So here is the result of multiplying those two 3 by 3 matrices. It is another 3 by 3 matrix. And if you clean up these entries, one plus 0 is 1. 0 minus 2 minus 0 is minus 2. 0 minus 0 minus 4 is minus 4. 0 minus 3 minus 0 is minus 3. Let's see, did I make a mistake here? This should be row 2, column 1. Yeah, I'm sorry, this should be the 1, row 2, column 1. Okay. So this is a 2. And then this is 2 times 0 minus 3 times 1 minus 6 times 0. So that will be 0 minus 3 minus 0 is minus 3. And then this guy is 0 minus 0 minus 6. This guy is minus 3 plus 0 plus 0. This guy is 0 plus 6 plus 0. This guy is 0 plus 0 plus 15. And this is the matrix A that we started with. And if we did the matrix multiplication in the other order, with I3 on the left instead of on the right, we would get the same thing. So this matrix with all ones on the diagonal and 0 everywhere else really does have the same property that the number 1 has. If you multiply any matrix by that matrix, by I, then you get the matrix you started with back. Which means we can define something like the reciprocal of a matrix. That's what this means. So a little note. When the size is implied, we just write I instead of like I2 or I3 or so on. And what we've just shown, or just seen, is that for any matrix A, I times A is equal to A, and A times I is equal to A. That is, I works like the number 1. But for matrices. So if I want to say what the reciprocal of a matrix is, if I want to divide by a matrix, I'm now ready to write down at least something that would make sense. Thus, what we need to solve the matrix equation AX equals B is another matrix A inverse with the property that A inverse times A, like 1/2 times 2, that should be equal to I, and A times A inverse should also be equal to I, where I is the appropriately sized identity matrix. Imagine you have such a thing. If we have such a matrix, then beginning with AX equals B, the matrix equation that we know is equivalent to our linear system, we can multiply on both sides by A inverse, and we do so on the left. This is like dividing both sides by the matrix A. This is the closest thing we have to dividing by a matrix. Because on the left-hand side, A inverse times A is the identity. So we get IX equals A inverse B. And then I times X, because I is the identity, is the same as X itself. So the matrix X, that 3 by 1, or that column of solutions, can be found by calculating the inverse of the matrix A times the matrix B, and that is multiplied on the left. So if you can find A inverse, then you can solve the system. And you can do it in a single step like this. And that's pretty hot shit. How do you find such a matrix? This becomes the big challenge now, right? So we can re-express our system as the matrix equation AX equals B. I know I can get rid of the matrix A on the left-hand side here, isolating X if and only if I can find this new matrix A inverse, so that when I multiply on both sides by it, I just get X over here. Finding an inverse is, unfortunately, exactly as much work as solving the system through any other means. And I know that that's an unappealing answer, because I'd like to get to this stage and say, okay, now here's like the super speedy way to get matrix inverses. And you never have to bother doing any sort of row reduction again. But in fact, the way you find the inverse matrix usually is precisely through row reduction. I want to pause for just a second before I get into the calculations to find an inverse matrix, because I know I'm not quite my normal self this morning. Are there any questions about the logic that we're trying to run through here, what the identity matrix is? How the identity works, or what this thing that we're looking for, A inverse, is, or its significance in solving the system?
I think I'm following, but the identity matrix is just the 0, 1, 0, like.
Yep. Yeah, the identity matrix, the n by n identity matrix, is just the matrix like with ones along the main diagonal and zeros everywhere else. Okay, so the big question at this point is, given a square matrix A, right, like an n by n, how do we find A inverse? And the answer is you start by augmenting A with the identity matrix of that same size. So that means my matrix A goes over here. I put the same size identity matrix over here. And you run row operations until you have the identity matrix on the left. Right? The same sort of things we were trying to do to solve our system. Clear out everything beneath the top left entry, make those 0, then make that top left entry 1, and continue clearing out everything except the stuff on the diagonals, then make all those diagonal entries 1. After you do that, the matrix that shows up on the right will be the inverse. So I'm going to show you an example with a 2 by 2, and then an example with a 3 by 3. And then I will give you a sort of shortcut for finding the inverse of a 2 by 2 matrix. It's the best I can do. It's the best anyone can do. So a problem like this will show up on your take-home test. solve the system. Here, I'm going to do just a 2 by 2, 2x minus 5y equals 15, 3x minus 6y equals 36 by writing it as ax equals b, finding a inverse and solving the matrix equation. All right. So first I need to see what is the matrix A, what is the matrix X, what is the matrix B. A is the regular coefficient matrix, which here is the 2 by 2, 2, -5, 3, -6. X is my matrix of solutions of variables here. It's the single column with 2 entries, X, Y. And B is the column of right-hand sides, 15, 36. So this matrix times this matrix equals this matrix. That is AX equals B. And that is equivalent to this system. I want to find, so with these, our system is equivalent to the matrix equation AX equals B. I want to solve that matrix equation. Now we're going to find A inverse. To do that, I take the original matrix A and I augment it by the identity, in this case, the 2 by 2 identity. So A augmented by I2 is 2, -5, 3, -6. Sorry, I put a solid line there, I've been using dotted lines. And I2 is the matrix 1, 0, 0, 1. And if I want to find the inverse of that matrix A, I need to run row operations until this is the identity. And then A inverse will be the thing that shows up over here. That's what we're describing here. So if I want to I want to make the identity show up over here. That means I want a 1 here, I want a 0 here, I want a 1 here, I want a 0 here. First thing I'm going to do is swap rows 1 and 2. This is one of those row operations we don't use a lot, but it's nice here. Because now if I multiply through the first row by 1/3, this will become a 1, this will become a -2. I'll get 1, -2, 0, 1/3. And row 2 stays the same, 2, -5, 1, 0. My next row operation would be to knock out this 2 down here. And in order to do that, I'll say my new row 2 is my old row 2 minus 2 copies of my row 1. In other words, I'm going to multiply this row by -2 and add it to this. Row 1 doesn't change. -2 times this plus this is 0. -2 times this is +4 plus this is -1. -2 times this is still 0 plus 1 is 1. -2 times 2/3 or 1/3 is -2/3. We're adding that to 0, so -2/3 is what goes there. Now, I can multiply through row 2 by -1. I'll make this a +1. Row 1 will stay the same. 1, -2, 0, 1/3. And row 2 will become 0, +1, -1, +2/3. And then my last step is to kill this guy. So if I multiply through row 2 by 2 and add it to row 1, that will do the job. So my new row 1 is my old row 1 plus 2 times old row 2. Row 2 doesn't change. 0, 1, -1, 2/3. 2 times this is 0 plus 1 is still 1. 2 times 1 is 2 plus -2 is 0. That's by design. 2 times -1 is -2 plus 0 is -2. And 2 times 2/3 is 4/3. 4/3 plus 1/3 is 5/3. And now I'm done. Because the matrix on the left is the identity matrix now, right? We started with A on the left and the identity on the right. Then we did row operations until the identity showed up over here, which means this is A inverse. A inverse is the 2 by 2, -2, 5/3, -1, 2/3. And that means I'm ready to solve my matrix equation. Now, AX equals B. If I multiply on both sides by A inverse, I get A inverse AX equals A inverse B. A inverse A is the identity. IX equals A inverse B. And that means X is A inverse B. Just like the matrix equation we solved the other day, only this one involves multiplication of matrices and inverses. A inverse times B is -2, 5/3, -1, 2/3 times the matrix B, which is 15, 36, this column. And then I can actually do that matrix multiplication. This is a 2 by 2. This is a 2 by 1. -2 times 15 is -30 plus 5/3 times 36. 36 divided by 3 is 12. 12 times 5 is 60. So -30 plus 60. And then the entry down here is -1 times 15 plus 2/3 times 36. So that's -15 plus 2/3 times 36. Again, 36 divided by 3 is 12 times 2 is 24. So this is the column of solutions. -30 plus 60 is +30. -15 plus 24 is +9. So the matrix of solutions X is 39. In other words, the solution to our system is X equals little x equals 30, and little y equals 9, or the ordered pair 30, 9, like this. 7, a little before 7. 8:47. Yeah, it was a little bit before 7. I wasn't looking at the clock, but I remember my alarm going up a little bit. All right. So that's it. That's us solving a 2x2 by finding inverse matrix and then operating on the matrix equation AX equals B with the inverse matrix to get your solution. Obviously, 2x2s can be solved much faster using other methods, just regular old elimination with the system, or even substitution is acceptable for a 2x2. I use this example as our first example because it's an easy example, or a relatively easy example. We understand 2x2s pretty well. I'd like to also do an example with a 3x3, and then I'll show you some shortcuts for finding matrix inverses. Because this procedure, right, if you look where all the time was spent, all the work was done finding A inverse. If somebody just handed me this inverse, then all I'd have to do is multiply these things together and boom, there's your solution. Again, in the same way that elimination is the superior method because it generalizes, you can use elimination on a system of any size. This is a nice method because it generalizes. You can use this method on systems of any size. And as the systems get larger and larger, solving them this way makes more and more sense. Let's do a 3x3, and I'll try to find a nice one. That's a little unpleasant. This is not the end of the world. Yeah. Same thing. Let's solve the system. X minus 2y minus 4z equals 0. 2x minus 3y minus 6z equals 3. And negative 3x plus 6y plus 15z equals -6. And we're going to do this in the same fashion we solved the last system. We're going to write out the matrix equation. Let A be the coefficient matrix, 1, -2, -4, 2, -3, -6, -3, 6, 15. Let X be the column of variables, little x, little y, little z, and let B be the column of right-hand sides, 0, 3, -6. And we know that X is going to be A inverse times B. So we're going to find A inverse. We seek A inverse. To find the inverse of a matrix, you augment it by the appropriate sized identity. A is a 3x3, so I will use the 3x3 identity matrix, I3. So that's 1, -2, -4, 1, 0, 0. 2, -3, -6, 0, 1, 0, -3, 6, 15, 0, 0, 1. There she is. Remember what we want to do. I want to make the identity matrix show up over here. In other words, I want to make everything down here 0. I want to make this a 0. I want to make this and this a 1. I want to make these guys up here zeros, and I want to make this a 0. To get rid of the 2, I can say that my new row 2 is going to be my old row 2 minus 2 copies of my old row 1. So I'll multiply by -2 and add to this. That'll kill him. And I'll kill the 3 here at the same time by saying my new row 3 is my old row 3 plus 3 copies of old row 1. And what I get, row 1 stays the same. -2 times this plus this is 0. -2 times this is +4 plus -3 is 1. Oh, that's nice. -2 times -4 is +8 plus -6 is +2. -2 times this is -2 plus 0 is -2. -2 times this is 0 plus 1 is still 1. -2 times 0 is 0 plus 0 is still 0. So there's that first row operation. And now for the row 3 thing, I'm going to multiply this by 3 and add it to this. So that gives me 0. 3 times -2 is -6 plus 6 is 0. Ooh, I'm lucky here. 3 times a -4 is -12. -12 plus 15 is +3. 3 times 1 is 3 plus 0 is 3. 3 times 0 is 0 plus 0 is still 0. And 3 times 0 is 0 plus 1 is still 1.
Which 3 are you multiplying by that they're positive?
So the 2 operations here that I'm looking at this row operation right now. So I'm going to multiply through this row by 3 and add that to this. I'm adding 3 times row 1 to row 3. So 3 times this plus this is my 0. 3 times this is -6 plus this is also 0. 3 times this is -12 plus 15 is 3. 3 times 1 is 3 plus 0 is 3. And then these guys are both 0. So these times 3 adding to this doesn't change anything. All right, we got really lucky there in that when we cleared out these 2 things, we got a 0 here and a 1 here. That saves us some time. My next move would be to get a 1 here. So my new row 3 will be 1/3 my old row 3. Rows 1 and 2 don't change. Just dividing everything in row 3 by 3, multiplying everything in row 3 by 1/3, leaving everything else the same. So I've got my 1s on the main diagonal. I've got 0s everywhere beneath. I just need to get rid of these guys and this guy. So to knock out this 2, I would multiply row 3 by -2 and add it to row 2. So my new row 2 is my old row 2 minus 2 times row 3. And while I'm here, I'm going to nuke the 4 also. We're going to multiply row 3 by 4 and add it to row 1. So my new row 1 will be my old row 1 plus 4 copies of row 3. Row 3 is the only row that's not going to change this time, so I'll write him down 0, 0, 1, 1, 0, 1/3. -2 times this plus this is still 0. -2 times this plus this is still 1. -2 times this plus this is now 0. -2 times 1 is -2, plus -2 is -4. -2 times 0 is still 0, so that's going to stay a 1. -2 times 1/3 is -2/3. So this is 0 plus -2/3, which is -2/3. That is the row 2 operation, the first operation I've got. Killing the 4 is going to be similar. 4 times 0 is 0, plus 1 is still 1. 4 times 0 is 0, plus -2 is still -2. 4 times 1 is 4, plus -4 is 0. 4 times 1 is 4, plus 1 is 5. 4 times 0 is 0, plus 0 is still 0. 4 times 1/3 is 4/3, plus 0 is 4/3. And now we're almost done. Just have to get rid of this 2. And I'll do that by adding 2 times row 2 to row 1. In other words, my new row 1 will be my old row 1 plus 2 times my old row 2. Rows 3 and 2 don't change. So I'm going to multiply row 2 by 2 and add it to row 1. So 2 times this plus this is still 1. 2 times 1 is 2, plus -2 is 0. That's what we were doing. 2 times 0 is 0, plus 0 is still 0. 2 times -4 is -8, plus 5 is -3. 2 times 1 is 2, plus 0 is 2. And 2 times -2/3, oh, interesting, is -4/3. When you add that to +4/3, you get 0 up here. Wasn't expecting that. But now we are done. Now we're done, because the thing on the left, this is now I3, which means this has to be A inverse. So the inverse of the matrix A is the 3 by 3, -3, 2, 0, -4, 1, -2/3, and 1, 0, 1/3. Right, that matrix on the right. So now we're ready to solve the system. So therefore, our matrix of solutions, X, we know will be A inverse times B, which is -3, 2, 0, -4, 1, -2/3, 1, 0, 1/3. And B was our right-hand side, 0, 3, -6. So if I carry out this matrix multiplication, I will get my column of solutions. Let's do it. -3 times 0 plus 2 times 3 plus 0 times -6. That's just 6. -4 times 0, 0 plus 1 times 3 is 3. I'll write this one, 3. And then we've got plus -2/3 times -6. So that's plus 2/3 times 6. I'll just write it so I can get it down. Then my last guy is 1 times 0 plus 0 times 3 plus -6 times 1/3. It's -6/3 is -2. And here we have this one calculation to do. 2/3 times 6 is 4, right? 6 divided by 3 is 2, times 2 is 4, 4 plus 3 is 7. So this is 6, 7, -2. And that's your solution to the system. The solution is, if you want to write them separately, little x equals 6, little y equals 7, little z equals -2. For the ordered triple, 6, 7, -2. So this is kind of the full story. This is as much of the story of linear systems as we could possibly tell you in a pre-calculus class. The place this goes next is starting to think of matrices as functions. And we ask, what sort of things can we get out if you take a matrix A and you multiply by the column X, Y, Z? In other words, what sort of right-hand sides could you put over here and still get a solution? But that is getting into the actual material of a linear algebra class, which is not a part of this course. So in this course, we intend to introduce you to the core ideas. How are systems and matrices related? What sort of row operations can you do to a matrix and just getting comfy doing those row operations? Solving a linear system by working with it as a matrix expression, either the augmented coefficient matrix, like we were doing last week, or this approach, where you write down the matrix equation AX equals B and solve by finding the inverse matrix A inverse. The very last thing I want to share with you about matrices is kind of a shortcut for finding the determinant, a shortcut for finding the inverse of a 2x2 matrix. All right, so you wouldn't, 2x2s should be able to solve those quickly. If you're going to use this matrix approach, you don't want to have to go through that procedure of augmenting and row reducing. So this a shortcut for finding a inverse when A is 2x2. Suppose the matrix A is the 2x2 A, B, C, D. And AD minus CB is not equal to 0. So if you multiply this by this, minus this times this, that thing is non-zero. Then the matrix A has an inverse and you can calculate that inverse as 1 over this number, AD minus CB, times the new 2x2 matrix you get by switching these with each other and negating these. So it'd be D negative B negative C A. It's a nice sneaky trick. Right? It's a quick way to find the inverse of a 2x2. I want to draw your attention to the second sentence here. Then A has an inverse. Not every matrix has an inverse.
What is written after and the equation?
And this says A inverse is equal to 1 divided by AD minus CB. That's why I said I need this to not be 0, because I'm going to divide by that number, times the matrix D, negative B, negative C, A.
And the first equation, sorry, is that AD minus
AD
C?
minus CB is not equal to 0. So a little quick note before I let you go. This is the last bit of material that I'm going to share with you for the semester. So, not all matrices have inverses. Only square matrices have a chance at having an inverse. But plenty of those don't have them either. In fact, if you take the coefficient matrix for any dependent or inconsistent system, if you have a system of equations that has no solution or has infinitely many solutions, and you try to calculate the inverse for the associated coefficient matrix, you will run into trouble. If you're dealing with a 2x2, that would mean this number right here is going to be 0, which means, okay, we can't use this formula. And you might ask, is it possible to find an inverse some other way? Well, yeah, you could try using the normal procedure, the one we did in the example before last, but you'll run into an issue there too. As you row reduce, you'll either get you'll get a row of all zeros. It will be impossible to make the identity show up on the left. Matrices which do have an inverse are called invertible. And invertible matrices are the matrices we like to mess with, given the choice. But plenty of matrices do not have an inverse. And the way you will detect that is when you try to go through the procedure for finding the inverse, right? When you try to go through, let's say, this procedure, instead of getting to this place, you'll get something like 0, 0, 0, right? Making it impossible to ever put a 1 in that position. And that would mean that the matrix you're working with doesn't have an inverse. Now, there is a tool for detecting whether a matrix is invertible or not called the determinant. But determinants really aren't something that belong in this class. I'm not going to push you on determinants. I am going to, content-wise, leave it here. So, congratulations. You have made it through to the end of MAC 1140. This is it. There's one little bit of extra stuff I want to share with you. Like I said, the notation for sequences and series, it's something we haven't gotten to in this semester, and that's not the end of the world. It is not normally a large part of pre-calculus. It's usually just a day or two. And the only reason we introduce it in this class is so you've been exposed to the notation, because you will see some capital sigmas at one point in Calc 1, and you'll see a lot of them in Calc 2. And life is just easier if you've seen the notation before. So I will do one more thing as far as delivering content goes, and that is I will record a little lecture on sequences and series for you to show you that notation. And then that will be it. So the things I need from you as the semester winds up here, these last few days, what you guys need to do is finish the homework. there's a homework set that I've posted for you to do with 10.3, 10.4, and 10.5, which is, working with matrices and finding inverses, that sort of stuff. Prepare for the final. Go back over any old homework that you didn't finish. Go back through your old tests. Make sure that you are comfortable with the problems from the old exams, comfortable with the problems from the homework and the quizzes. And then the last thing I need you to do is make sure you complete the take-home exam. So I'll be posting that a little bit later today, exam 4, which is on systems. There will be an honor pledge at the top there that says, I swear I didn't do any shady shit. Shady shit here would mean like looking up problems online, using any apps on your phone, talking to a classmate or tutor or anybody else about the problems. Those would all be things that you cannot do. So complete that take-home test, complete it on your own, and then make sure to scan and submit the completed take-home before you come to the final exam. So you'll have several days to work that. That is it from me, gang. I'm working on grading your exam 3s. I know everybody wants those back, but it's just that time of the semester. I got shit piled up from here to the ceiling. So I will get those done certainly before the final as soon as I can, so you can get those grades and no longer be wondering about that. Is there anything else that you guys would like from me in parting here? Calc 1, right now I am teaching a Calc 1. I think in the spring I'm doing one. It's a good question. Let me take a quick peek at my schedule. I think so.
I think it's like 2 to 3:15 Monday, Wednesday, Friday with the lab in there.
Let's see here. So yeah, Monday, Wednesday, Friday, 2 to 3:15 is exactly correct. Yeah, and that's a sync class. That's a Zoom class like this one. Yep. Okay. The section number there, if you need it, is 004. That's the Calc 1 I'm doing in the spring. Any other questions or anything else I can answer or help you guys with before we sign out for the day? Alrighty then, I'm going to go ahead and sign off here. I hope you guys have a lovely rest of your day. Please remember to work on those things. Work the homework, complete the take-home test, do that honestly, and then review the homework, quizzes, and past exams to prepare for the final. If you do need anything from me, anything comes up, you're curious, want to talk, whatever, you guys know how to get a hold of me, Canvas, Discord, email, all that. Office hours, have a regular office hour today, 1 to 2 p.m. Otherwise, I will see you guys for the final. Take care.